Finishing out Chapter 6 with Section 6.6, we've got the law of cosines. Unlike the law of sines, the law of cosines can be helpful for finding unknown sides and unknown angles within a given triangle. Again, I'll just leave you to read the proof in the text, but there's a few different variations on it that we can see. We're going to start with the same basic notion. Capital A, B, and C for the sides, little a, b, and c for the opposite sides. And the proof of this one actually starts on the Pythagorean theorem. It looks at some distances. We get a squared equals b squared plus c squared minus 2bc cosine A. So a squared, b squared, c squared, the usual formulation from the Pythagorean theorem, but because this isn't a right triangle, we don't know that's true. Minus 2bc cosine of A. You can actually plug this in for a right triangle where A will always be pi or pi over 2 or 90 degrees, and it'll work out really nicely there too. But we can rewrite this no matter which of these pieces are unknown. It's essentially the same formula, but I could have b squared equals a squared plus c squared minus 2ac cosine b, or c squared equals, I guess I'll write it as a squared plus b squared minus 2ab cosine of c. So in each one, this angle here was the angle opposite this side here, and the two pieces left over were what were multiplied there, there, and there. So another way of computing these things, let's try a triangle where all we know is the sides and we need to find the angles. So how about it's 2, 4, 5 triangle. Probably not a right triangle, and I will label these guys A, B, and C. And I know that if I need to find A, 4 squared should equal 2 squared plus 5 squared minus 2 times 2 times 5 times cosine of A. I've got 16 over here, and if I put this together, I've got 29 minus 20 cosine A. Subtract that, I've got negative 13 equals negative 20 cosine A. So 13 over 20 was cosine A. And now we need to use our inverse functions again to get that the inverse cosine of 13 over 20 is equal to A. And let's do this one in degrees. You get that it's about 49.46 degrees, or about 0.863 radians, depending on which one you wanted. Now that allowed us to find A. I'm not going to go through the procedures for B and C. It's exactly the same thing, just using the other formulations of the law of cosines. The most common application that we see to this, at least written into your textbooks, is when you're looking at more than one body in motion. So oftentimes when you're looking at two different runners going different directions, or two different cars going different directions, they have one of them going this way, one of them going this way. They're always putting them at these nice 90-degree angles because it makes it easy to compute. Well, actually let me move this so it's a little bit further over. Something we can end up with, suppose you've got two ships. One of them's heading that direction, and the other one's heading that direction. So I've got one east at 35 miles an hour. And I've got the other one 30 degrees west of north at 45 miles per hour. So what that really means, east, we're heading this way, north would be up here, another 30 degrees west of north, and a lot of navigation is measured in degrees. We haven't quite gotten into radians yet. Means that this angle is 120 degrees. Now, if they started at the same point, so let's have them both start right here at the origin, and let's find the distance apart after 1 hour. So what we're really being asked is, can I find that? And we certainly can, because this is going to boil down, so I eliminate all those coordinate axes, it's just solving a triangle. And we know that after 1 hour, that has length 35, and this has length 45, and there's our unknown that we're trying to solve. Keep it in red. So, applying the law of cosines. Whoops, did not mean to erase that. There we go. We've got this unknown, we have the angle opposite this. So the law of cosines, correctly applied, would be x squared equals 45 squared plus 35 squared minus 2 times 45 times 35 times cosine of 120. So I've got, let's see, 45 squared is 2,025, 35 squared is 1,225, and 2 times 45 times 35 is 3,150. Cosine of 120, that's going to be the same thing as cosine of 2 pi over 3, and since we're over here in this quadrant, cosine should be negative, so we're going to get negative 1/2 for this cosine value. Compute all that out, and we're left with x squared is 4,825. So x is the square root, 4,825, which if you plug that into a calculator and round it off, you get it's about 69.46 miles. So something like this that couldn't be worked out with just the Pythagorean theorem, because this line here and this line here, because these two ships aren't moving in perpendicular directions. And as you might imagine in real life, if you're trying to work out a model for things that are moving, very rarely do they move in perpendicular directions. So you would end up needing to use the law of cosines there. That'll do it for Chapter 6. So we should be able to finish up the Chapter 6 homework. In the next video, we'll move into Chapter 7. It's going to take us back to some of the trigonometric identities we saw in Chapter 5, and we'll be expanding that notion to help us solve trigonometric equations.